Okay, this is a video about refraction, and a really good question to ask for any new concepts you've learned is what happens when you push it to the limit. So we're going to push refraction to the limit in two situations, and hopefully we're going to discover something interesting. So to start with, we're going to have this is a barrier between, say, plastic, which is more optically dense, and air, which is less optically dense. That's in relation to each other. So if we're looking at the refractive indexes, the N of air is going to be much less than N of plastic. Okay, so from that we're going to have the normal. Let's try and be consistent with our colours so it's easier to see what's going on. Red's going to be my normal, and we're going to have a range of light rays coming in at different angles. So we've got blue here. I'll do it in a slightly thicker line so it's clear. Here's our standard through the centre. Remember, it's going from a less to a greater density, optical density, so it's going to bend towards the normal, and we measure it by the angle between the normal and the incident ray. So that's going to be one point. What about if we, I'll stick with a thick line, if we approach it along the surface of the block? So this might be the edge of a glass block here, and it's approached directly along the surface. Well, we can't really bend because we're not striking it on the surface, so I'll just carry on straight through. So no change there. And the other extreme is what happens if it comes in, so that's a 90-degree incident angle. If it comes in along the normal, it's just going to carry on going straight through. And as you can imagine, if we had one further ray coming in on the other side, it's just going to be a mirror image and repeat. So this ray is going to bend towards the normal that way. So that's that one there, just to make it clear. So it's really important when you're learning your physics that you're not just looking at a static diagram. You want to see the diagram develop so that you can see, because if you look at this diagram now, it's a mess. But from the start you could see how it's constructed. So that's refracting from a lower to a higher density medium. So the next situation we want to consider is when we travel out of a more dense medium. So let's draw our medium again here. This time I'm going to see if I've learned something from the previous diagram. This time we're going to have, say, plastic on this side and air on this side. So air has the lower refractive index, and we need our normal, and I'm using the thicker lines for this because it's going to be easier to see when I draw the thinner lines. And let's use these colours just to make it different. Okay, so this time your classic ray that is coming in like that, it's going to bend away from the normal. Okay, so previously it would have gone closer to the red line, now it's going closer to the blue line. Okay, so that angle there is larger than that angle there. Okay, that's not the focus, so I'm not going to draw any more to do with that. We're looking at pushing this to the extremes. Okay, same thing again if we come in along the normal, it's just going to go straight through. You could work that out using Snell's law. The sine of 90 degrees is 1, so there's not going to be any modification to the refractive index and to any of the parts of the equation. You can work that one out yourself in your own time. So the other way we could do it is going further out here, and there's going to be a point that we get to where when it refracts away from the normal, it's going to run along the surface. Okay, I'll just go over that a couple of times so you can see it. So that's our refracted ray when it's up here. Now if we go beyond that, we're going to strike a little bit of an interesting situation. There's a good colour that we can use for that. I'll try this colour. If we go beyond that, Okay, there's nowhere for it to refract to, because we've already gone along the surface. What will happen is that we'll have something called total internal reflection. Okay, that angle there is meant to be the same as that angle there. It's just not to scale. I'll draw this diagram again shortly to show you. So there's a point, we call it the critical angle, okay, and this point is the angle beyond, move across a wee bit more, beyond which, so beyond this angle, total internal, in this case internal to the plastic, reflection. Occurs. Okay, so going back to the diagram, when we increase the angle of incidence, when we're going from a higher to a lower density substance, we bend away from the normal. If we increase the angle enough, it'll reflect inside, because there's nowhere else for the angle to refract to. Notice I'm using the words reflect and refract. And the point right at the boundary of this, where just before total internal reflection occurs, we could say it refracts along the surface of the outside surface of the object. That is the critical angle. So in this case, it's marked by the green one here, and this angle here, remember the angles are all measured from the normal, that is our critical angle. Very important concept. Very important for things like fibre optics, and I'll just grab a picture for that. So you can see this is a plastic tube, and there's a laser light that's bouncing along on the inside, and it's totally internally reflecting off each of those surfaces in there. This is very cool. This is how communication over long distances overseas occurs now. It's cheaper and faster than communicating by electricity. We can instead send a beam of light down, so it's very, very cool, very, very useful. Another use you might have noticed if you have a cell phone screen or a wristwatch is that you can look at it on a really, really sharp angle, and there'll be total internal reflection off the rear surface of that screen, and you can actually turn it into a mirror. We used to sit there staring at our wristwatches on funny angles and using it like spies to observe what's going on behind us or in places where we can't obviously see. It's like a non-obvious mirror. Anyway, let's just quickly redraw this diagram to recap. So we've got I'll draw this out in full. This might be a glass block, and we've got our normal on the outside there, and we're going to have a light ray, go for orange. Somehow it's ended up inside the block. Could be a laser light shone inside, and it's going to bend. If you increase the angle, it'll reflect on the inside, so that this is no good with different colors, but this angle here is the same as this angle here. So I'll just label that ray 2 and ray 1 here. Ray 1 is going to refract probably along the surface. It depends on the substance as well, each substance you have, and then ray 3, which really should be ray 1. Ray 3 is just going to be outside here. Okay, depending on the substance you have, you'll get a greater or lesser critical angle. We can do a quick calculation using Snell's law in a later video. I'm going to do it now because this video is already extended too long. But you just use theta c, your critical angle, in place of theta 1 or theta 2 in your Snell's law. N1 sine theta 1 equals N2 sine theta 2, and you use your 90 degrees here as your angle of refraction, and that tells you what the critical angle is. So there we go.